There you go. Hi, everyone. Time for a little organic chemistry. Today, we're talking about Proton NMR, which is also known as H1 NMR, which is also known as nuclear magnetic resonance spectroscopy of the first isotope of hydrogen. Yeah, let's do this. So we're looking at key concepts. Unit 4, Part 4, the last of the series in this unit. And proton nuclear magnetic resonance. So remember, the whole goal, the main goal of Unit 4 is to figure out what a molecule looks like. We're trying to figure out its structure. We're trying to do structure elucidation. And we've seen mass spectrometry, IR spectroscopy, carbon-13 NMR, and now it's hydrogen NMR. 4 techniques, I guess 5 techniques if you include depth NMR. That's sort of like, it is carbon NMR. Anyways, but 5 techniques give us 5 different sets of data to help us figure out what a molecule looks like. Okay, and of those 5, I would argue that this one is the most helpful. Cool. All right, so let's break this down. Back in carbon NMR, we saw that there was 2 features of the data that we had to look at. We had to find the positions of the peaks. That has to do with functional groups. And we had to count the number of peaks. That has to do with the equivalent carbons. The main idea being that every carbon produces a peak, but sometimes 2 carbons produce a peak that overlap because of the same distance away from the nearest pi bond or electronegative atom. In other words, those carbons are equivalent. Okay, don't forget that information, because that same exact type of information shows up here too. But we also get 2 more pieces of information. Bottom line, carbon NMR gives us 2 things to look at: position and number of peaks. H1 NMR is going to give us 4: position of the peaks, the number of peaks, the integration of the peaks, meaning how many hydrogens produce each peak, and finally something called splitting of peaks. And splitting tells us something about the neighboring hydrogens. We'll save that one for last. Okay, let's look at the key concepts here. Let's see if I'm forgetting anything. We're getting 4 pieces of data because nearly all the hydrogens, 99% of them, as far as we can tell, are hydrogen that do not have a nuclei. I'm sorry, do not have a neutron, and they all H1s absorb radio waves, and we get a lot of good data. Unlike carbon atoms, most carbon, 99% of them, are carbon-12, and they are NMR silent. They don't absorb radio waves. We don't get good NMR data. We don't get any NMR data from them. One isotope of carbon, carbon-13, 1% of all the carbons, very low number, 1%. Yeah, they absorb radio waves. So we do get data from the carbon-13 isotopes in our molecule. So that's the biggest difference here. Carbon NMR doesn't give a lot of data. Position and the number of peaks is what we can ascertain. Hydrogen NMR, oh boy, almost all, 99% of the hydrogens give us data. So now we got 4 pieces of data. Okay, let's look at those 4. First, we got position. Sure, why not? Position of the peaks. Okay, just like in the carbon NMR, you will get a correlation table. And the one I'll supply to you on exams looks like this: correlation table saying, hey, if you get a peak around 0.7 to 1.3, it's probably a methyl group or a primary hydrogen, right? We're looking at hydrogen, not carbon. And then remind you, it's right up here. So on your correlation table, it'll have this title. It'll be exactly formatted just like this. I'm just going to photocopy this, cut and paste this right onto your exam. Okay, so this table says hydrogen NMR. Well, at least says hydrogen, not NMR. But the position tells you something about the functional groups, right? So if you get a peak around 2.2, well, it could be a hydrogen next door to a ketone, or 2.2, it could be a hydrogen next door to an alkene. That's an allylic hydrogen. But you know what? Just like in the carbon NMR, the correlation table, we had to be a little flexible using it. You will have to be flexible here too. So if the peak's at 2.2, you You might say, wait, 2.2 doesn't look like in this range. It's actually close enough. 2.2 says maybe it's a hydrogen on a carbon next door to an arene, right? AR, that's a match. Aromatic compound, we're talking about benzene, an arene. Over here, we got aryl, which means, hey, hydrogen's directly on the benzene ring. They're way downfield. They're shifted way downfield. 6.5 to 8 is a typical range. Again, average range. There you go. Cool. And because the hydrogens are so close to the double bonds, the pi bonds of the benzene ring. Let's see, what else we need to know? Yeah, all in bold print and italicized. Just saying correlation table supplied. Yes, unfortunately, it lists average values and it is often inaccurate. So this is your guide. This is suggestions, not hard fact. Correlation tables can be useful, but be flexible in using them. If you really want better data about functional groups, hopefully you have the infrared spectrum. Or if you're doing research, go acquire the IR spectrum of your unknown compound. That could actually do a better job of figuring out which functional groups are in your molecule. Oh, and there's another note here. It is very common for peaks to overlap. So that is unfortunate. If you look at the range here, TMS, the reference compound, starts at 0, and we can have peaks right next to it. So they're pretty close. And the highest, farthest downfield, I should say, 11 or 12, that's not that far. Carbon NMR, we can get peaks all the way down to 200. So things got spread out in the carbon NMR. Hydrogen, not so much. That's unfortunate. Finally, last note about position of peaks. What do you do when a hydrogen's next to 2 or more functional groups? The table only lists typical or average values for a single functional group. Well, here's some data. What is this? This is methyl chloride or 1-chloromethane. Hydrogens are next door to 1 chlorine. The value measured in the lab is 3.05 ppms, the position of the peaks. Parts per million is actually what this means. You can take a look at the introduction to NMR to see a better explanation of ppm and delta, the chemical shift. That's how we measure the position of the peaks. Anyways, real data for this molecule, there's a single peak. All 3 hydrogens are equivalent. They're the same distance from the chlorine because they're all on the same carbon. There's a peak at 3.05. Does that make sense? So let's scroll down here to 3.5. Well, here's 3.05. No, that's next to a hydrogen next to an oxygen, hydrogen on carbon next to oxygen. There we go. Between 2.5 and 4 hydrogens next door to a halide. There. Okay, so that does make sense. What if there's 2 chlorines next to these hydrogens? The correlation table says, well, for 1 halide, 2.5 to 4 is typical. But the real answer is when there's 2 chlorines, now we're at 5.32. So what's happening here is it's kind of adding up. 1 chlorine shifts a hydrogen downfield to 3. So 2 of them, well, maybe it should double that. We expect maybe it should shift down to 6. 1 chlorine shifts at 3, and the next chlorine shifts at 3 more. Well, not really. It's not exactly 6. It's 5.3. And you might guess, well, what if you have 3 chlorines like you do in chloroform? Oh yeah, we saw this reagent in one of the reactions of an alkene to make a cyclopropane ring. Chloroform here, put that molecule in the NMR, and the actual value is at 7.25, not 3 times 3 here, right? So it's somewhat additive. Yeah, more chlorines farther downfield, but the correlation table is not going to help predict that, hey, if you have 3 chlorines, it's 7. No, you might be led astray. If you go to 7, you might say, oh, that's a hydrogen next to a benzene ring. No, it's not. Here's the actual molecule. Yeah. So again, correlation table, be flexible, be careful with it. Enough said about position for now. Second point, let's look at the number of peaks. We did that in the carbon NMR. In carbon NMR, we said that sometimes two carbons would generate a peak that actually stack, overlap, and make for a bigger peak. That's still true in hydrogen NMR. What was happening is that two carbons were the same distance to a pi bond or to an electronegative atom. So those two carbons got shifted downfield by the same amount. So then they overlap. Hydrogen, same deal. Now it's going to happen quite frequently because to be the same distance away from a functional group pi bond, another way of saying the same thing is to talk about molecular symmetry. If the molecule is symmetric, then there's a carbon on one side, another carbon on the other. That's what makes carbon equivalent. Same is true for a hydrogen, right? If you can split a molecule in half, there'll be hydrogen on one side that look like the mirror reflection of hydrogens on the other side. They're equivalent. They should be the same distance to the functional groups. They'll have overlapping peaks. One more thing, though, is that it's not just splitting it, a twofold symmetry, a mirror plane symmetry. We also can get rotational symmetry. So let's look down here at this methyl group on benzene. I got 3 different ways. I just found this off the internet. 3 different ways of drawing this molecule. There's a benzene ring with a methyl on it, benzene ring with a methyl, and benzene with a methyl. These three hydrogens, 1, 2, 3. You might say, oh, if you cut it in half this way, this hydrogen is equivalent to that one. They're on either side of the mirror plane. Yeah, but what about this hydrogen? It's not reflecting. Yeah, it doesn't satisfy the twofold or mirror plane symmetry. It satisfies rotational symmetry, right? So you can rotate about this bond so that this hydrogen goes up here, this one goes down there, and that one goes over here. And now what was on top is now on the side, mirror reflection of that one. And you can rotate again. So, right, single bonds are free to spin. So these hydrogens can be rotated about all different ways, such that they're all equivalent to each other. And oftentimes students are like, do I really have to worry about rotational versus mirror plane symmetry? And the answer is no, not so much. It's better to just realize, hey, all 3 hydrogens are attached to the same carbon. So that's a better way of predicting equivalence. If you just see that, let's keep doing that, clean up. You can see that all 3 hydrogens here are attached to the same exact carbon. That makes all hydrogens the same distance away from all the other functional groups. And these hydrogens attached to the same carbon should be giving the same peak, overlapping peaks. But for every rule in chemistry, right, there's always an exception. The big exception are alkene hydrogens. So if you have a carbon-carbon double bond, you have a couple of hydrogens here, you'd say, hey, looks like there's a plane of symmetry here, and these hydrogens are attached to the same carbon. And I would agree. I would expect those hydrogens to give the same peak, overlapping peaks, because they're equivalent. But what if we put an electronegative atom here? Now, this hydrogen and that chlorine are cis to each other, where these are actually trans, and the double bond prevents rotation. This hydrogen is always physically, if you take a ruler, physically farther away than this one. This hydrogen is actually closer, right? Cis groups are more crowded, they're closer together. So it turns out these are no longer equivalent. So that's the big exception. It's the only one. Ooh, I hope that's the only one. I should double check my exams before I make them, before I hand them out to students. But I'm pretty sure that's the real only exception. I'll let you know if there's another one. Just to reiterate, hydrogens attached to the same carbon usually are equivalent, produce the same peak, overlapping peaks. But here's an exception, alkene hydrogens. Okay. Here's another common problem in hydrogen NMR. Sometimes different non-equivalent hydrogens or different peaks, they may be so close together that they appear to be one peak. So here's an example of a molecule called toluene. That's an old common name for methylbenzene. Yeah, no one says methylbenzene. They all say toluene. We'll see that later in organic chemistry. Okay, here's the data. Carbon NMR, same molecule, methyl group on benzene. Hey, so we're looking at carbon NMR. How do you know the x-axis goes up to 200 or around 200, sometimes 220? But that helps identify that this is the carbon data. So we're getting peaks from just carbon atoms. Toluene has 7 carbons. I expect 7 peaks, but they're only 5. Why are there only 5? We're missing 2. That's because we have some overlapping peaks. We actually have equivalent carbons, right? So there's a plane of symmetry here that this carbon and this carbon are the same distance to the methyl group. Yeah, they're both producing peak 2, this one. And then we have carbon 3. Well, that's this carbon, that carbon are lying on either side of the mirror plane. They're equivalent also. They're the same distance to the methyl. And it turns out that they're barely separated here. You can actually see that they're 2 different peaks, just barely. We might have to zoom in to get a better view. Anyways, and that's just because methyl is not very electronegative. It's not electronegative at all. It's just different. These carbons are a little bit closer to the different part of the molecule, the methyl, than these, but that's not the electronegative. There's no pi bond on methyl. It's not that big of a split in terms of sending it downfield. Now let's look at hydrogen. Same molecule, same exact molecule, but now we're going to tune the radio waves so that carbon doesn't absorb them. Instead, the hydrogen atoms, or the nuclei of the hydrogen, absorb the radio waves. How do you know this is the data for hydrogen? The x-axis is around 10, 12, something like that. It's more compressed, right? 200 is more spread out, so that peaks that are close together have a chance to be seen as separate peaks. With a scale of 10, things are much more jam-packed together. These 2 hydrogens are equivalent. They're still a mirror plane. They're the same distance of methyl. We expect them to be equivalent. But these 2 hydrogens are equivalent to each other, but not to this one. We might say that this is peak A, this is peak A. This should produce a second peak, but this hydrogen should produce the same overlapping peak. A and B should be different from each other. They're different distances from the methyl. Problem is, with such a small scale, the peaks actually are overlapping just because they're just too close together. In fact, this hydrogen is also overlapping in here too. So we get only 2 peaks, right? So this is the property we're looking at. How many peaks are we getting? Carbon NMR, we saw 5. There's 7 carbons, so it tells us, hey, 5 doesn't match 7, so we have some equivalent carbons. Here we have 2 peaks, darn it. And how many hydrogens? We got 1, 2, 3, 4, 5, 6, 7, 8. There's 8 hydrogens. We only have 2 peaks. There's a lot of equivalent hydrogens. And in fact, there's some hydrogens that are not equivalent. Hydrogens that are marked with an A versus hydrogens marked with a B. They're not equivalent, but they're also overlapping. Darn it. Just something to look out for. Okay, enough of that. Those are the 2 qualities, peak position, number of peaks, same 2 qualities we saw in carbon NMR. Now it's time for something different. Intensity. Actually, that's not quite true. Let's go back up here. Intensity of peak. So actually up here in the carbon, we did see this. It wasn't quite reliable, so we couldn't use it as strongly as we can in hydrogen NMR. What are we talking about? Well, carbon 2 and 2 over here are producing this peak that's labeled 2. There's 2 carbons producing that peak, so we expect the peak to be bigger because each carbon produces a peak, and there's 2 of them. They're overlapping, standing on top of each other. We expect that peak to be taller or larger, more intense. We got carbons labeled a 3 here. There's 2 carbons producing or overlapping to make 1 big peak. Yeah, that's this one here. It's also a lot larger, a lot bigger, more intense than the others. But in carbon NMR, it wasn't exactly proportional, right? there's one carbon producing this peak, and this carbon is just producing this peak, and that's kind of nice. These two are the same height. This looks proportional. Peak 4, wait, 4 is this carbon. Wait, I got 1 here. 4 is down here, sorry. Hey, bottom line is there's one carbon producing this peak, but look, it's twice as big as the other. It's not 2 carbons because it's twice the height. No, carbon NMR intensities are not reliable. It's suggestive though. The biggest peaks contained equivalent carbons. There's 2 carbons producing each of these peaks, but there's only 1 carbon producing this one, even though it's twice as big as that. Switching to hydrogen NMR, now the intensity of peaks is reliable. And in fact, we asked the computer that's collecting the data to measure the area. Has anyone taken calculus? What's the procedure for integrating? That's right, you integrate the area underneath the curve. So you can call this information intensity, because the bigger the peak, the more hydrogens must have produced that peak. Or you can call it integration, because literally that's what happens. The computer does calculus to figure out how much area is under each curve. And what it'll do is it'll plot an integration curve, this curve right here. And the height is proportional to the area. This line is called the integration curve. Here's a peak. Here's a peak over here, and that's it. Well, there is a third peak, but it's tetramethylsilane, the reference peak at 0, so we ignore that. There's 2 peaks, but you can see that this height is larger than that height, telling you there's more hydrogens producing this peak. But if you just look at the heights, it's not actually proportional. It's not a good measurement. It's actually the area under the curve that's proportional to the number of hydrogens. Unfortunately, it can't actually tell you exactly how many hydrogens. It can only report ratios. So we just know, the computer knows that the area under here corresponds to an area, a relative area of 3 at chemical shift 1.2. Yeah, this peak is at 1.2. The peak at 1.2 has a relative area of 3, whereas the peak at 3.65, yeah, there's 3, here's 4, this 3.65 here. The peak at 3.65 has a relative area of 1. Or in other words, one peak is 3 times the area as the other. So we know there's 3 times as many hydrogens. Here we actually have elucidated the structure. We've been told what the structure is. We have 9 hydrogens, all the same distance to the pi bonds and oxygens. They're all overlapping, they're all equivalent. 9 H's are producing this peak, the bigger peak, right? Dennis, look at the colors. It's nice color coding. These 3 hydrogens are producing this peak. 9 versus 3 is in a 3-to-1 ratio, and that's what the areas are telling us. That there's 3 times as many hydrogens in this peak as that one. And then it's up to us to figure out, oh, it's not 3 hydrogens and 1 hydrogen. The molecule actually has 9 and 3. Okay. What else do we have to know about peak positions? There's 2 ways that you can get the intensity, the integration. The best way is when the computer actually reports it as a number. And on exams, a lot of times I will give it to you as a number. There's also a chance I might give it to you, the integration value, as this integration curve. So what you want to do is just eyeball it. So you can see that the line starts here and ends here. And so your mind just kind of says, well, it looks like about this high is the value of the number of peaks here. And then just say, well, that's about from here to here. I'm just eyeballing it. It's the same distance as that. From here to there, same distance. And then from here to there is about the same distance. Yeah, top of that. It looks like 3 times as high as this one. So the area is roughly 3 times as this, or 3-to-1 ratio. And if you're doing it by the eyeball approach, make sure you realize, hey, the area is approximate. Be a little flexible with that. And even if it gives you the numbers, sometimes you have to be flexible with that. Now, when we get to the sample test, I'll try and narrow it down, be a little more clear on this. I'll try and give you more definitive numbers. Okay, but if you go in the lab and actually use our NMR and collect real data, okay, if you're collecting real data, no one's there to tell you exactly what's happening. You're going to have to be flexible with your integration values so you can actually figure out what the molecule truly is. I got a little note over here on the side. That was a student. I can't remember who I thought I'd just share with you. TMS properly stands for tetramethylsilane, which is this molecule, but they like to rename it the most shielded TMS, because it's the farthest up peak, farthest upscale peak. Upfield is the word. I thought, oh, that's clever. The most shielded, farthest upfield. Everything else is downfield, de-shielded. Yeah, so the farther downfield, that means the electrons that were shielding the hydrogens have been pulled away by the electronegative atoms, right? So these hydrogens are close to this oxygen. They're 2 bonds away. So the hydrogen has 1 bond to carbon, the second bond to get to the oxygen, they're 2 bonds away. Whereas these hydrogens are 1 bond, 2 bonds, 3 bonds, 4 bonds away to the hydrogens. 4 bonds away from the pi bond. They're not as affected as much by those electronegative atoms and the pi bond. They're not de-shielded as far. Closer to electronegatives atoms, the more de-shielded, the farther downfield they are. That's actually going back to peak position, sorry. All right, we're on integration. Let's have a little more fun with that. Here's some real data. So I wanted to kind of go over integration, but some real data in case you need to do this in the lab. Again, this is a lab type question. On the exam, I'll try and give you better, more accurate data. Okay, so what are we going to do with this? Well, we're only going to look at integration here. We can look, I'm not going to try and figure out what the molecule looks like. Let's just focus on integration. Okay, so what have we got? We got no numbers reported. That's too bad. We have to estimate it. So if you look at where it starts to where it ends, that's how many hydrogens. Let's just say it's 1. 1 hydrogen is producing this peak. And now we kind of eyeball it over here. And then you just kind of eyeball it. And I think that's a little short. Right? Again, I'm kind of eyeballing it from here to here is 1, here's 2, and this is higher. What I'm trying to do is estimate how high this is relative to the first one. And so I knew I was going to have trouble with it. So I actually cut and pasted those integration curves and made them stack together. So in the lab, you'd actually take a ruler and measure the height of the integration curves. And there we go. So there you go. So that's what I've done. And actually, I estimated pretty well. I could tell that it's more than 2, but less than 3. But we got the little note over here, the area might be approximate. Okay, so then the question is, how many hydrogens are here? Because it looks like, where am I going to put this? Let's put it down below. And let's give myself a little more room. There we go. Okay. Integration looks like it's 2.5 to 1. Doesn't it? I mean, if this is 1, there's my 1. And then if I stack this 3 times, well, it looks like it's about half, so 2.5. But it's an estimate, so maybe it really is a 3 to 1 ratio. Again, if you take more, if we had a chance to go in the lab, we talked about how to use a machine to tell it to integrate this a little bit better. And ideally what you want is a flat baseline here where it doesn't have any peak. And you can see there's a slope to it, a little bit of a slope there. Definitely there's a slope up here. And that's what you don't want. You want it to be flat to get a more accurate integration value. Anyways, That's in the lab artifact, something to worry about in the lab. Right now, interpreting the data is what I want to cover. Hopefully you see that this could be 2.5 to 1, or since it's approximate, maybe it really is 3 to 1, and the data just isn't lining up that well. So we might actually be 3 hydrogens to 1 in our molecule. Or maybe it's an exaggeration. Maybe this should not be as high as it is. Maybe it's really 2 to 1. So that's what you'll do for real data in the lab. Make your best estimate, but be flexible. And then some of you are probably saying, wait, how can you have half of a hydrogen in a molecule? I know, you can't. Instead, it's a ratio. So let's double this. Instead of 2.5 to 1, maybe it's 2 times 2.5, which is 5. And we'll double this. Maybe the actual ratio is 5 to 2. And here's an example of a molecule that has 5 hydrogens, all attached to benzene. So maybe they're all overlapping. So one single peak might add up to 5. And then there'll be 2 hydrogens on a different carbon. And then maybe there'll be, I don't know, bromine here or something. So this molecule actually does produce a ratio of 5 hydrogens in one peak, 2 hydrogens in the other peak. Or maybe it's 3 to 1. Let's see, 3 to 1. Let me look at my sample problems. Is this the one? Yeah, that's the one we did earlier, right? Right here, thank you. That had a 3 to 1 ratio. So maybe there's a molecule that actually does have a 3 to 1 ratio. Another molecule that had a 5 to 2 ratio. Or what about 2 to 1? Let's see, what if we put 2 hydrogens on one carbon, 1 hydrogen on the other, and then we sprinkle, let's see, other groups on here, maybe some chlorines. Okay, so now every carbon has 4 bonds. And this carbon, sorry, these hydrogens are on the carbon with 1 chlorine. This hydrogen's on a carbon with 2 chlorines. So these hydrogens are different. This one should be sent farther downfield. It's closer to electronegative atoms than these hydrogens. They're only next door to 1 chlorine. Next door. They're kind of like in the same house. They're both attached to the same carbon. Anyways, I hope you see that these are not equivalent. 2 chlorines on one, or on the same carbon as the 1 hydrogen. 1 chlorine versus 2. And yet, these 2 are equivalent. They're attached to the same carbon. They're the same distance to all the chlorines. 1 hydrogen is not different from the other. That should produce 1 peak with the area of 2. The second hydrogen produces 1 peak, a second peak with the area of 1. Okay, just to reiterate, trying to approximate the areas, be flexible, and it is possible to have relative areas of 2.5 to 1, 3 to 1, or 2 to 1. The trick is to get the actual chemical formula. This one, let's see, it looked like this, right? Something like that. So this is the 3 to 1. It was actually 9 to 1. Sorry, 9 to 3. It could have been 6 to 2. I have to find a different molecule that says 6 to 2, but this one's 9 to 3. So how would you know which ratio it is? Oftentimes you get the chemical formula. So if the chemical formula is C7H7Br, and you saw these ratios, and you're like, well, which one is it? Well, it has to be a ratio that can add up to 7. Well, 5 plus 2 equals 7. Yeah. 9 plus 3 equals 12. Hey, this molecule is C6H12. 12. Oh, there's 12 hydrogens, and 9 plus 3 equals 12. 2 plus 1 equals 3. Yeah, because this molecule only has 3 hydrogens. It has 3 chlorines. So look at the total number of hydrogens in the chemical formula, and from your ratios, see if you can find a ratio where you can add up the numbers equal to total. That'll help you figure out which ratio it truly is, right? Cool. All righty, enough of the integration or intensity of peaks. Really important, but perhaps even more important is this new phenomenon called splitting. Where did I put it? Right here. Splitting of peaks. Okay, this indicates a number of neighboring hydrogens. That actually might be the most valuable aspect. I'm reading right off the slide here because we're trying to figure out what the molecule looks like. So it would be really helpful to figure out, hey, you got some hydrogens. Who is right next door to them? How many hydrogens are adjacent to these hydrogens? And splitting gives you that information. Okay, let's break this down theoretically and then experimentally, meaning what do you do with the data? First, let's talk about theoretically, how does the data show up? So you really don't need this, but I know some students find it useful. If you understand how the data is created, it can help you understand it and help you interpret the data and get you to the answer a lot faster. Okay, so what are we doing? We're going to talk about hydrogen producing a peak and then that hydrogen having some neighbors. So let's start with no neighbors, the simplest case. No neighboring hydrogens, H's. That might be a case where there's a carbon and a single hydrogen. Oh, there might be more, could be equivalent. Let's simplify it. This hydrogen is sitting here, you shine radio waves on it, it produces a peak. All the hydrogens need to produce a peak. And then the other carbons, well, they're bonding 4 times, but they're either to other carbons or an oxygen, a halide, maybe there's some double bonds in here. The point is, adjacent to this hydrogen are no hydrogens, no neighboring H's. So you just get a simple peak, right? That's an ugly peak, but there it is. At some peak position. That's what that's my x-axis here. Single peak, and we call it a singlet. Single peak, it's not being split, it's called a singlet. Now let's put a neighbor. One neighboring hydrogen. So we got the same system. We got this hydrogen who's going to produce a peak. And let's put a neighbor over here. But only one. All the other bonds don't have hydrogen. So this hydrogen is going to produce a peak. Based on the other functional groups, the position of this peak should be at the same location. So I'm trying to line this up. So I'm going to draw the peak of this hydrogen where it's showing up. It's going to show up here. But what effect does the neighbor have? Let's go back to the theory a little bit of why the peaks are sent downfield or upfield. That's because of shielding, right? We said that if an atom, in this case hydrogen, is closer to electronegative atom or a pi bond, those electrons are being pulled away, deshielding, and exposing the nuclei to a stronger magnetic field. The magnetic field of the instrument, the NMR spectrometer. And the stronger field sends it farther downfield, right? That's the key. Stronger magnetic field, due to the stripping away of the electrons by electronegative atoms and the pi bond, sends the signal, the peak, downfield. Okay. Nuclei, hydrogen in this case, has spin in the nucleus, right? We talked about that in the theory that the hydrogen, when the nuclei, that is, absorbs radio waves, the spin will flip, right? It flips upside down, and then it'll flip back up. Okay, so the radio waves get absorbed, and that's the energy that flips it upside down. Okay, this hydrogen is going to produce a peak too. Let's not worry about that for a second, but just realize that sometimes the spin of this nuclei is still up. Let's put it down here. So the neighbor, and don't put a double arrow, let's put a single barb arrow. That's usually how we indicate the spin. So when this hydrogen hasn't absorbed radio waves yet, the spin's going to be pointing up. And it turns out the external magnetic field is also pointing up. So the little nuclei acts like a bar magnet and increases, right? The net magnetic field felt by this hydrogen is the sum of the two magnetic fields, the external spectrometer's magnetic field, and a little extra magnetic field from this hydrogen's magnetic moment of the spin pointing up. So this hydrogen is not going to be absorbing radio waves exactly at this peak. It's going to be a little bit downfield. But you know what? Sometimes this hydrogen has already absorbed radio waves, and it might be pointing upside down. Then this hydrogen is going to feel a slight reduction of the magnetic field, right? The magnet of the spectrometer is pointing up, and then this hydrogen has its magnetic moment pointing down, and so that actually subtracts it a little bit. So sometimes it's going to produce a peak up field, less magnetic field strength. And what we get is two peaks from one hydrogen. The original peak was then split into two. We get a doublet of peaks. And that's splitting. And now if you look at the data, hey, I got a doublet here. That's telling you the hydrogen that produces that peak has one neighbor. Cool. All right, let's do another one. Maybe two more. What if you have two neighbors? Two hydrogens are neighbors, and you can choose to put the hydrogens on different adjacent carbons. You know what? This could be a tertiary carbon. Maybe there's hydrogens on this carbon, but let's say there's a total of two. So I'll put both of them on this one. And we're still asking, hey, where is the position of this peak? Well, now you have two hydrogens. And remember, you don't analyze just one molecule in the NMR. You put a whole bunch of drops or a whole bunch of crystals, dissolved it in the solvent. You got a lot of molecules in there. Maybe a whole mole, probably not that many. But you have a lot of molecules. So in that whole collection of molecules, one of the molecules might have the two hydrogens both pointing up. And what happens then? Well, the external magnet's pointing up. These are pointing up. They're going to be farther downfield than this peak, right? So the center line, try to line it up, will be here. And when those two hydrogens, the neighbors, are both up, the peak's going to be farther downfield, like right here. Sometimes, however, one will be up, the other will be down. And why is the first one up? No, the first one could be down, and the second one could be up. That's the other possibility. But in either case, the magnetic field strength is going to cancel out as if there were no neighbors, right? And so now the peak position is based solely on the external magnet. It goes back to where it was before its original position. So when the two nuclei have opposite spins, you're going to get a peak here. And in fact, there's two possibilities of that happening, whereas there's only one possibility of them both being up. So the area is going to happen twice as often because there's two chances for it. And of course, the fourth possibility is that both spins are pointing down. That's going to both subtract from the external magnet and send the peak upfield. And there's only one chance for that, just like there's only one chance for the first case, both up. So the peak area should be the same for those two, but double for the middle. Also, if you total all the area, it equals this area, right? One of the attributes of the hydrogen NMR is that the peak area tells you how many hydrogens are there. So the area of this corresponds to one hydrogen. If you add up the area of all three of these, that's also equal to one, because these three peaks are being produced by this hydrogen. It's just being split into a triplet by the neighbors, right? Two neighbors makes it a triplet. Okay, what if you have three neighbors? Again, you put those neighboring hydrogens on any of the adjacent carbons, but you could put them all on the same one, make it a neighboring methyl group. So we're asking, hey, hydrogen, what does your peak look like? How does it split? And next door, on the carbon next door, on the house next door, well, how many neighbors live next door in that house, on that carbon? 3 hydrogens. So what are the possible spin orientations? Well, they all could be pointing up. First one could be up, second one down, the other one up. See, first up, we can have this up and this one down, and then we can have, that's it, this one down, this one up, that one down, this one down, this one down, this one up, and finally down, down, down. That should be everything, right? Okay, these three really add up. And so center line's right there. And three of them is going to shift it farther downfield than that one. So maybe right here. There's only one chance for that. We have 2 up, 1 down, 2 up, 1 down. That's it. 2 up, 1 down means there's a net total of 1 up, which is the same as this one. But there's 2 chances for it. So it should be twice as high. Look at the spin combinations here. There's 2 down, 1 up, 2 down, 1 up. That's a net total of 1 up. So it's going to send it up this way. And we got 2 chances versus 1. That's why I got this peaks twice as high. And then there's only 1 chance for all 3 of them to be down. That's going to send it the farthest upfield to the right. The area should be the same as this one. Only, there's only 1 chance for these. If you have the whole area, the area still has to equal 1 because 1 hydrogen is making the peak. It's just that 1 hydrogen is now being split by 3 neighbors into a quartet. Barbershop quartet, 4 singers, triplets, 3 babies, triplets, 3 peaks. There you go. Doublet, twins, 2 peaks. Nice. Okay, so there you go. And then you can keep going after that. However, on exam, we're not going to. If you have more than 4 peaks, you can just call it a multiplet. More than 4 split peaks, we're going to call it a multiplet because you'll notice that the peaks on the edge are getting smaller and smaller. And it turns out that you split more and more, there's a chance that these peaks will be blending into the background. Unfortunately, the background is not perfectly flat. It's sometimes a little noisy. And so this peak might be difficult to tell apart from some of the noise peaks. So anyways, once you get beyond 4, let's just call it a multiplet and just know that there's a lot of neighbors. Let's see, I got this other graph down here. For those of you who like math, you might be noticing the pattern here. What was the pattern? We start with 1 hydrogen gives you 2 split peaks. 2 neighbors can give you 4 possibilities, but 2 of them combined, right? The magnetic field canceled out. You get 3, but the ratio is 1 to 2 to 1. And then we have these 6 possibilities, but a couple of them are the same. So you have a ratio of 1 to 2 to 2 to 1. That's Pascal's triangle. It's just interesting, not on the exam, but it's just how we can mathematically predict the size of those split areas. And here's some examples down here. Here's a triplet. That's when there's 2 neighbors. Here's a quartet. That's when there's 3 neighbors. If you have 4 neighbors, n equals 4, then it's split into a pentet. Again, we're just going to call it a multiplet on the exam. Sextet, that's when there's 5 neighbors and 6 peaks. And you got septet, octet, nonet. Yeah, keep on going if you like. But here's the problem. If you have so many neighbors, those edge peaks are going to be really hard to see. And they're going to be untrustworthy. And that's what's predicted by Pascal's triangle. The outermost has a relative area of 1. The innermost has a huge area. This is 70. This is 70 times bigger than those peaks. Yeah, even this one, 20 times bigger than those peaks. That might be hard to see. And even 6. This peak is 6 times the areas of those peaks. Those peaks may be pretty close to the baseline. It might mistake, yeah. We're just gonna have to say, or you look at this and say, well, is there one more peak? I don't know. Well, that's another reason why we're just gonna call it a multiplet. So on the real data, once you get past 4, it's going to be untrustworthy. We're just going to call them all multiplets after that and realize there's lots of neighbors. and neighbors are hydrogen. No other element counts. There's an exception if you take advanced organic chemistry. But for this class, just the hydrogens are neighbors. Oh, so if you're looking at the data, then you have to figure out how many neighbors are there. So the way I learned it is n neighbors produce n+1 rule. I'm sorry, n+1 peaks. That's the n+1 rule. So if you look at this, there's a quartet. That's 4. n+1 equals 4. So what is n+1? Good grief. n+1 equals 4. So what's n? N is 3. You have 3 neighbors. Students have better ideas. I love their ideas. There was a different student from the TMS idea where it's the most shielded TMS. Someone else said the peaks, think of them as me and my neighbors. So me meaning, hey, there's a hydrogen who's being split. So let's say this peak is me and I'm with my neighbors. 1, 2, 3. 3 neighbors. Oh, I like that. So if you say, hey, here is me and my neighbors, there are a total of 3 peaks, but one of them is me and the other 2 are my neighbors. Okay, you gotta be a little careful. That's a great way to figure out that a triplet means 2 neighbors. But remember that the middle peak is not the true hydrogen and the other ones are peaks from the neighbors. It's all one hydrogen being split, right? The theory is up here, saying that quartet is all 4 of these peaks is due to this hydrogen producing peaks, but then the neighbors split that 1 peak into a quartet, into 4. That's the theory. But you can look at the quartet and say, oh yeah, that's me and my neighbors. There's 3 neighbors. That's the way to remember it. Okay, my neighbors. All right, let's look at some real data. That's the theory. Let's put it into practice. Let's figure out what a molecule looks like based on 4 attributes of the hydrogen NMR: the position, the number of peaks, the integration, and the splitting. Okay. That's a lot of data. So you might want to build a table to organize the data to help you decipher, decode the data so you can figure it out. There's actually more information than just hydrogen NMR. We got the chemical formula. So what I like to do first is just count up the degrees. Let's see what we're dealing with. How many rings and pi bonds are possible? So number of carbons is 3. So the number of hydrogens, if this was saturated, would be 2 times 3 plus 2 more, minus, how many does it actually have? 7. And then how about adjustments for halides? Halides and hydrogen, we'll start with the letter H. Count halides like hydrogen. So I know I got 7 actual hydrogens, but bromine, I'm gonna count you as if you were a hydrogen. Oxygen looks like the number 0, so don't adjust for oxygen. Nitrogen is negative. Subtract 1 if the nitrogen shows up. And then divide the whole thing by 2. So we got 2 times 3 is 6, plus 2 is 8. Minus 7 plus 1 is also 8. Ah, that's 0. It is saturated. That means no ring and no pi bond. That is terrible handwriting. Sorry. Cool, only single bonds. That's all we got. Actually, with only 3 carbons, you could probably make some educated guesses as what the molecule looks like. That's one strategy, and to see if it fits the data. Here's another strategy. Let's organize the data. First, let's look at the number of peaks. Well, there's 1 here. So look at the baseline, get this peak. And then right here, I got a bigger peak. That's peak B. What's been done here is that, and you don't always get this information, but we did here. Someone zoomed in on this peak so you could see all the splitting. So this is a zoomed in portion of that peak. Same is true here. We'll deal with that in a few minutes. First, we got the number of peaks. There are 2. There's peak A and peak B, 2 peaks. So there's 2 equivalent hydrogens, but there's 7 H's. So there's a lot of equivalent hydrogens in here, giving us these 2 peaks. Okay, That's the number. Next would be position. So peak A is about what? 4, and then just a guess. That's about 4.5. That's about 4.25. Let's just say 4.2. And you can write ppm, or I'm going to use a delta scale, the little Greek letter delta to represent the position. What's this peak? Peak B is about, I don't know, 1.7? I don't know, something like that. It's an estimate, right? What are you going to use the position for? For comparing on the correlation table. Grab that. There we go. Here's the correlation table. You're going to get this on the exam. We had what, 4.2 and 1.7. Well, 1.7 says it's close to hydrogen, close to a double bond. Wait, but our molecule's saturated. So again, be careful with the correlation table. Here's 1.7. It says just a tertiary carbon. Yeah, but 1.7 could be secondary. And even primary is close enough. So be flexible. Don't say, oh, it must be tertiary. Wait a second. There's only 3 carbons. How can you get all 3 carbons attached to the same carbon if you only have 3? You need 4 carbons, so you attach 3 to them to make a tertiary carbon. It's impossible to have a tertiary carbon with only a molecule with 3 carbons in it. Okay, so be flexible with the correlation table. We also had a peak at 4.2. Yeah, you might say 4.2 sounds like a hydrogen on an oxygen, or hydrogen on a carbon next door to oxygen. That's close to the 4.2. Yeah, but who are you going to trust more, the correlation table or the chemical formula? I trust chemical formula. There's no oxygen in here. Yeah, so where's a halide? Halide is bromine. So typically, on average, hydrogens attached to a carbon that also has a halide should give a peak around 2.5 to 4. Ours is at 4.2. So there's a hydrogen on a carbon next with the same carbons attached to the bromine from the chemical formula. And this hydrogen is producing a peak at 4.2. And then these hydrogens that produce peak B are not attached to a bromine. Sorry, I'm not saying that right. The hydrogens are attached to a carbon, and that carbon's not also attached to bromine because it's farther upfield. These hydrogens are farther, let's say H's, farther from the bromine based on the position of 1.7. They're farther upfield. 4.2 is farther downfield. They're closer to the electronegative atom. Okay, we dealt with 2 attributes of the spectrum, NMR spectrum. We have the peak position and the peak numbers. Now let's look at integration. Well, they did report the integration curve, so we could try and guesstimate that height, but why? Over here is better data. We're actually told the ratio. So relative area of 6 for the peak at 1.71, well, that wasn't far off. This one's 1.71, that's peak B, and there are 6 H's here. So sometimes on your NMR data, I will just write 6H above the peak. On peak, the peak at 4.28, now 4.2 or so, 4.28, there's 1 hydrogen producing this peak. How come it's not a ratio 1 to 6? Isn't it 2 to 12? Or is it 3 to 18? No, there's only 7 hydrogens, right? And 1 plus 6 equals 7. So yeah, this is exactly 1 hydrogen. Nice. Okay, so let's write that. Put it in our table. That peak A is being produced by 1 hydrogen. Peak B is being produced by 6 hydrogens. And hey, this hydrogen is attached to the same carbon as the bromine. So we got some good data already. Starting to figure out what the molecule looks like. Last bit of data is the splitting pattern. So now I kind of pretend I am the hydrogen and I am me and my neighbors, 1, 2, 3, 4, 5, 6. Technically, we're still going to call that a multiplet because I don't know if these peaks on the edges are real. We will in a minute. What about this splitting pattern for peak B? I see 2 peaks. This is a doublet. Okay, and what's the interpretation? Well, the doublet is me and my neighbor, one neighbor. So there's one neighbor here. And the multiplet has lots of neighbors. And then here's something cool to do. After you get the integration value, 1 and 6, after you get the number of neighbors, that neighbor value, lots in 1, see if you can crisscross. Yeah, there's a match. Lots matches this. This is actually 6 neighbors, right? We can trust the peaks. Yeah, this one hydrogen has 6 neighbors, and there they are. These 6 hydrogens have 1 neighbor, and there he or she is. There you go. So now we got to attach these together to make sense of this. And here's the bottom line. How are you going to make 6 hydrogens equivalent? One carbon can't hold all 6. No, a carbon can hold at most 3. Ooh, but what if you have a plane of symmetry so that 2 methyl groups with their 6 hydrogens are the same distance from the bromine? So we already know there's a hydrogen on the same carbon as the bromine. Well, if we put a methyl group up here and a methyl group down here, we put a plane of symmetry right here so that these methyls are the same distance to the bromine. They should give the same overlapping peak. That works. Well, let's see if the splitting makes sense. So let's go visit these hydrogens who live in this house. And out on the lawn, and there's the front door. So these 3 hydrogens are here playing, yay, on their lawn. I know I'm being silly. I like being silly. All right, so 3 kids here. They live in this house. In this house, right next door, there's 1 kid, 1 hydrogen. And over here, there's another house, and there's 3 kids here. Go outside and play with the neighbors. Hopefully they all get along. So these 3 hydrogens live in this house. This hydrogen lives in this house. These 3 hydrogens live here. So go ask this hydrogen, this kid, hey, how many neighbors do you have? This hydrogen looks up and down the street. Up the street, there's 3 neighbors over here next door. And down here, there's 3. There's a total of 6 neighbors for this 1 kid. Yeah, this hydrogen has 3 neighbors there and there. It is split into a multiplet. Now talk to one of the kids here. Hey, how many neighbors do you have? So this hydrogen, well, it's hydrogen. This kid says, well, down the street, there's no one living there. There's no houses. Up the street, there's 1 house, and there's a kid lives there. I have 1 neighbor. Yeah, these hydrogens have 1 neighbor, and it's this hydrogen. Same deal up here. Hey, how many hydrogens? Hey, talk to these hydrogens. How many neighbors do you have? We have 1 neighbor living next door. So that means the peak that these hydrogens make is split by 1 neighbor. It's going to be split into a doublet. And that's what happens. We see a doublet. Cool. Hey, that's the molecule. It's 2-bromopropane. We just elucidated the structure. Yay. All right, one last one for this video. Let's do a little bit more complicated one. But we'll follow the same tactic, same strategy. Let's break it down, look at 4 groups, 4 criteria, 4 factors. What do you want to call this? Let's look at the number of peaks first. Okay, so I like starting on the left side. You don't have to. I like using letters. You don't have to. However, you do get points for assigning peaks. So let me go get all my points. So this is pretty messy. Let's redraw it over here. So on the exam, it will usually say to assign all peaks for full credit. And what that means is label your peaks however you want with numbers or letters in any order. Maybe this is peak A and this is peak B for you, but put it on the graph so I can see it. And then put those same labels next to the hydrogens, assigning the peaks to the hydrogens. So, hey, hydrogen, which peak did you make? This single hydrogen produce peak A. I like putting circles around it so it's easier to see, but you don't have to, right? Just get your label close to the hydrogen. This methyl, that produced peak B. This methyl is overlapping and also producing peak B. I have now labeled all my peaks. I've assigned all the peaks. Peaks A and B, assigned all the hydrogens. Every hydrogen must make a peak. Where's the peak from bromine? It's not a hydrogen. It doesn't show up. Carbon, the scale goes to 10. We didn't tune the radio waves to absorb so that carbon could absorb radio waves. So carbon, you're not making any peaks here. It's only hydrogen. All right, so we'll also assign peaks. Maybe you can remind me at the end. All right, let's go and label our data. How many peaks? I got a peak here, second one there, third one there, fourth one here. Ooh, and zoomed in. And a fifth one here. Hey, there's a peak. No, ignore the TMS peak. That's not from this molecule. A, B, C, D, E. I'm going to put my little table down here. Okay, so let's just collect the data and then we'll analyze it. Position. The position is at 8-ish. I can just put 8. This one's around 7. You don't have to be that exact, right? Because we're going to use the correlation table very flexibly. Is that a word? We're going to be just going to estimate our values. This looks like a 3.7, 3.8-ish. Peak D is just a little less than 3, but I'm just going to say 3. And this is around 1.2. I don't know. You can put 1 if you want. That's a position. So I got the numbers, 5 peaks. I got the positions. Yep, we'll leave a little space so I can analyze it later. Let's get the integration. I'm looking up here for the answer. Where's the relative areas? Darn it, it's not here. Okay, so this is a case where we get the integration curve. That's this single long line here. And what you're doing is you're estimating by eye this height compared to this height from this line to that line. That looks about the same. So the integration appears to be 1H to 1H here. And this, what do you think? Is that quite 2? I don't think so. This looks like 2. That looks like 1.5 to me. And this one, that looks like 1. It's definitely smaller than this height, right? This height is bigger than that height. And that height looks like the same as these two. So I think that integrates to 1. And this looks like twice. Well, it might also be 1.5. Let's also say it's 1.5. Okay, what if someone said, no, I think it's, whoops. I think this should have been a 2. Yeah, you might have. That's okay. What you want it to do, though, is somehow add up to 12. So let's double these. 2 times that is 3. Let's double this one. Let's double this one to 3. And then let's double these. Okay, and let's add them up. 2 plus 2 is 4. 4 plus 3 is 7. 7 plus 2 is 9. 9 plus 3 is 12. Oh, we found it. We can do these just because it's here. 2 plus 2 is 4, plus 4 is 8, plus 2 is 10, plus 4 is 14. That's not a match. We only have 12 hydrogens. And that's how you do it. If you had the integration curve on the exam or in the lab. Just kind of play around with the, make your estimate, add them up, see what works. So we actually know there's 2 H's. I'm gonna circle it so it's clearer from the rest of my work, because you get partial credit for showing work. So don't erase stuff. I like kind of seeing your thought process. Yeah, 2 plus 2 is 4, plus 3 is 7, plus 2 more is 9, plus 3 is 12. Good, it's a match. We've got 4 things to analyze from the hydrogen NMR, but there's 4, last one's splitting. So go back here, peak A. If you need to, well, I don't know if you can, no, you can't zoom in on the test. You have to kind of hold it close, but I'm hoping you see it's a doublet. So splitting. It's a doublet. How many neighbors in a doublet? Me and my neighbor. There's just one neighbor there. Peak B, that's also a doublet. There's also one neighbor. These hydrogens, these two hydrogens have one neighbor. Peak C, these three hydrogens, how many neighbors do you have? Looks like a single peak. Yeah, it's a singlet. Singlet. You have 0 neighbors. D, that's hard to see, but I'm hoping you can actually see that looks like a quartet. And then the zoomed in portion, that definitely is a quartet. And how many neighbors does a quartet have? Me and my neighbors. So one of these is going to be me, and the other 3 are the neighbors. Lastly, peak E, it's really smashed together. Sometimes you don't get the zoomed in portion to see, oh, it's truly a triplet. Sometimes you just have to see that there's a peak here, there's a peak there, and look down here. No, I don't see any other peaks. One on top. Yeah, this is a triplet. And how many neighbors? Me and my neighbors, there's 2. N+1 rule, I see 3 peaks. N+1 equals 3, so N must equal 2. So for N, and neighbors. Okay, cranked out the data except for one other piece. Let's put in the degrees now. Degrees, well, there's 10 carbons. So 2 times 10 plus 2 more. Minus, well, there's 12 hydrogens actually, and 2 oxygens. Wait, that counts like 0 when we're doing degrees. 2 times 10 is 20, plus 2 is 22, minus 12, divided by 2. 10 over 2, that's 5. Ooh, anytime there's 4 or more, what functional group should you suspect? It's not a guarantee, it's just a suspicion. Benzene. Benzene has a ring and 3 pi bonds for 4 degrees, plus 1 more degree, which could be a ring or another pi bond. Okay, that's not truth. It's not proof or anything, but nature does like benzene. So, hey, so now we can tackle this data in any way, shape, or form. If you want to go right to splitting and work on that, you can. You think about the integration, you could do that. Position, correlation table, number of peaks, think about symmetry. But I just calculated degrees, and now I'm suspicious. Do I have any other data support that maybe we actually do have benzene? Well, go to the correlation table where some data talks about benzene. Well, if there's okay, I know the table says methyl, but what if you just have a benzene ring with a carbon that only has 1 hydrogen? There's another carbon. Where does this hydrogen show up? Next door to a benzene ring. It's still going to be in this region. So be flexible. It doesn't have to be methyl. It just says hydrogens on carbon next to a benzene ring should be in this range. But hydrogens on the benzene ring should be between 6.5 and 8. 6.5 and 8. Hey, 8 and 7. The peak positions are suggesting benzene. So I got 2 pieces of evidence suggesting benzene, the degrees of unsaturation and now the peak positions. I am strongly leaning to the idea that benzene is part of our molecule. And then let's just keep analyzing the correlation table. We got a peak at 3.8, 3.8. Well, it could be a halide, not from the chemical formula, right? Chemical formula says no halides. There's 2 oxygens though. All right, 3.8. What else we got? 3.8. Well, one of the hydrogens could be attached to oxygen. That would be 3.8. Too bad we don't have the IR, right? Alcohols have a great big broad peak around 3,400 reciprocal centimeters in the IR. So if you get the IR, that's where I would go. I would go and look at that, see if there's a big broad peak suggesting alcohol, because 3.8 could be hydrogens attached to oxygen, not necessarily carbon. Oh, wait. How many hydrogens are on peak C? 3 of them. Wait. If 3.8 means alcohol and I have 3 hydrogens, that means 3 alcohol groups, which means 3 oxygens. I only have 2. So this is out. That can't work. Maybe it's hydrogens next door to oxygen. That could work. 3.8 is that region. We have a pi bond. 3.8, 4.5. That's less likely, but it's possible. Let's just put that down. We got hydrogen next to an oxygen. So I'm going to rewrite this group. Hydrogen on carbon next door to oxygen. That's right in the range of 3.8. That makes a lot of sense. But maybe, put a question mark here, is it a hydrogen next door to another double bond? Not the benzene double bond. Remember, we have 5 degrees of unsaturation. There could be a second pi bond, maybe between 2 carbons. That's it. That's what the correlation table is suggesting, not saying for fact. Let's see, we got a peak D at 3. Okay, well, that's the same region. That could also be next to an oxygen. So put that in here. So these 3 hydrogens, there's 2 oxygens, so maybe they're different oxygens. Oxygen can bond 2 times, form an ether, right? So maybe on one side of the oxygen, there's an H, and the other side, there's a different H. And maybe one of those other H's is, well, this one, 3.8, maybe that's closer to the benzene ring. That has pi bonds that was shifted downfield. Maybe that's why they're not exactly overlapping, not a plane of symmetry there. Let's see, what else is 3 indicating? 3 could be at the, well, it's not a halide, where you said there's no halides. I don't think we have room for a triple bond. Hydrogen at the end of the triple bonds at 3, but if we're gonna go with benzene, we got 2 pieces of evidence suggesting benzene. A double bond, a triple bond rather, has 2 pi bonds, and we don't have room for 2 more pi bonds if we have benzene. So 3 could be a hydrogen on a carbon next door to benzene, or it could be on the other side of oxygen. Again, be flexible with the correlation table. Put a question mark there because I'm leaning towards that one, but this is still possible. 1.2, those are the alkanes, right? 1.2, yeah, these 2 are 1.2. Even 1.4 is close enough. Just an alkane. Based on position of 1.2, that looks like an alkane hydrogen. It's not close to much. It's farther from the benzene ring, farther from the oxygens. That's position. We kind of looked the correlation table. We're done with that. Integration. Okay, what we're going to say is, well, it's probably not an alcohol. So these hydrogens are on carbon. So we got, maybe it's a CH2 group, right? They have to be equivalent. So the easiest way is put both hydrogens on the same carbon to make them equivalent. 2 hydrogens on the same carbon, 3 hydrogens on the same carbon. Maybe that's a methyl group. 2 H's, 3 H's, that's another methyl. That's quite likely what those groups are. It's not a guarantee though. Wait a minute. So let's see if it's true for peak A and B. Is it true that there's 2 hydrogens on the same carbon and the carbon's part of benzene? Now, so here's benzene. Every carbon's already making 3 bonds, right? So this carbon's got a double bond and a single, 3 bonds. It only has room for 1 hydrogen. So this is actually a false assumption. It was the easiest way to make both hydrogens equivalent so they can produce the same peak. But the peak position, especially way downfield, that is suggesting a benzene ring. And the degree suggests it's a benzene ring. We probably do have a benzene ring. So the only way to get hydrogen to be downfield at 8, not the only way, one way to get hydrogen to have a peak at position 8 is to attach it to a benzene ring. And that means if there's two H's, I gotta have a plane of symmetry either here or there or somewhere to make it symmetrical. Same is true for peak B. Peak B is another hydrogen on benzene. Maybe we should write ARH. From the correlation table, an arene, benzene, an aryl hydrogen. Okay. Think if I kind of expended the integration for now. Let's look at splitting. Ooh, okay. So splitting, we want to crisscross. So this one neighbor should crisscross. Does it make sense that maybe on benzene there would be a neighbor? Yeah. In fact, how many total hydrogens are on benzene? Well, there's a peak A and a peak B, and peak A has two H's and peak B has two H's. And that's it. The only hydrogens on benzene are between 7 and 8. There's a total of 4. So why don't we just draw them all? What are all the ways that 4 hydrogens can be attached to a benzene ring? So, okay, take the shortcut. Maybe we got all 4 together. Maybe we have 3 together and 1 apart. What if we have 2 hydrogens together and the other 2 on the other side? And it turns out those are all the ways of arranging 4 hydrogens on benzene. And now we just count neighbors. So, hey, hydrogens. Hey, this hydrogen, how many neighbors do you have? Well, I live in this house. Go up the street. I see one neighbor over here. I see a second neighbor over there. I got 2 neighbors. So if you put this in the NMR, what is your splitting pattern, hydrogen? 2 neighbors. I'm a triplet. We don't have a triplet. So we do not have this arrangement. How about this one? How many neighbors do you have? I got a neighbor up here, up the street, and down the street. I live in this house, and the house next door, the other carbon, has 1 hydrogen living in it. Up the street, the other house next door, there's another hydrogen. Another way to think of neighbors is neighboring hydrogens are 3 bonds away. 1, 2, 3. Or, I like the house analogy. Carbons are the houses that the hydrogens live in, and the carbons are adjacent houses, right? So these hydrogens live on adjacent houses. Okay, this is also predicted to be a triplet, right? It has 2 neighbors. That ain't right. So it's gotta be this one. Yeah, so you talk to this hydrogen. Hey, hydrogen, how many neighbors do you have? Well, no one lives next door. It's a vacant house. But up the street, I got 1 neighbor. That's a doublet. Talk to this hydrogen. Yeah, my neighbor, there's an empty house, an empty field. I don't know. Over here, I got 1 neighbor. You both have 1 neighbor. Cool. There's also a plane of symmetry here. So these hydrogens can be equivalent. Maybe they're peak A. These hydrogens could be B. And there you go. That explained the splitting pattern. I know it didn't quite crisscross. I think they had exceptions. But hopefully this makes sense to you. Which is actually pretty cool. A doublet of doublets, downfield around 8 or 7, shows this, tells you it's this arrangement of hydrogens on benzene. Way cool. This is called para, by the way. We'll learn that later. This arrangement of hydrogens on a benzene ring is called para. This arrangement is called meta. This one's called ortho. And you don't have to memorize that yet. So not now. It's just interesting information. Okay, so based on this data, we have come to the conclusion that hydrogens are up here. And I'm going to say, let's say this. I don't know. Maybe this one. I'm going to put the electronegative oxygens over here because closer electronegative, if I got oxygens in the molecule from the chemical formula, it's going to shift them downfield. And B, it's got to be farther from the oxygen. So I'll try not to put oxygens on this side. This carbon and that carbon need a bond each. All right, what is this peak telling me? Peak C is a methyl group. I can either attach it to another carbon-carbon double bond, probably not. It's probably attached to oxygen. Put a little question mark there. Maybe. That's what the peak position suggests. It's a hydrogen on a carbon, carbon attached to oxygen. Well, integration says there's 3 H's here. It's a methyl group. Oxygen has one more bond. That's peak C. We got a CH2 group producing peak D. And that might be next to an oxygen. Put a question mark there. And what was the other suggestion? Maybe it's attached to the benzene ring. Maybe on this side. Away, I'm going to put oxygens on that side. That's another question mark. Peak E is a methyl group. I'm not sure where I want to put that. Probably over here maybe, or far downfield away from the benzene ring and the oxygens. What about the splitting? Well, this one is a singlet. So when you think about putting this methyl group, don't attach it to this group because that will make them neighbors. Don't connect this CH3 here or on this side because that will give it neighbors. Instead, why don't you connect this one? This methyl group could connect there because this methyl has 2 neighbors, which are right here. These hydrogens have 3 neighbors, which are right there. They crisscross. These are neighbors to each other. D and E are peaks from hydrogens that are neighboring. Also, peak D, this carbon has 1 more bond left to make. Carbon makes 4 bonds. I can't attach more hydrogens here, or a carbon with hydrogens, because that will give more neighbors. Awesome. Okay, that's what we got so far. What was the chemical formula again? C10H12O2, 2 O's. Okay, so maybe we have our 2 O's there. How many degrees of unsaturation do I have in my puzzle pieces? I only have 4. There's supposed to be another one. So I either have to get a ring in here, or what about a double bond to that oxygen? Because I kind of need to connect things to the benzene ring. So that's the other idea, is that maybe it's a double bond O and it's not a hydrogen on that double bond O because that'll be a position 10-ish. So maybe it's a ketone neighboring hydrogens around 2 to 2.4. And I know this is at 3, but let's be flexible. Maybe. Wait a minute, that's the other thing. How many carbons do we have? The molecule C10H12O2. I got 6 C's here. I got 1 more there. I got 1 more there, and I got 2 here. So 6, 7, 8, 9, 10. Good, I got all my carbons. So if I want to attach a double bond, right? 6, 7, 8, 9. Oh, I double counted. D is already here. Oops. Oops, glad I caught it. All right, so I connected these 2. Yeah, that's what I did. I said, okay, so I put them here, peak D. So I have 9 carbons. I'm missing a carbon. Yeah, it helps to draw things out. It's getting a little messy, but there's a carbon. And if I want to put the CH2 group next to benzene, I still have an oxygen. I need a double bond. I need a pi bond. So there's 4 degrees in this benzene ring, and now here's my 5th degree. No H's on this, so no peaks from this group. All right, so what have we got? Let's rewrite this because it's so messy. Right now I'm thinking there's 10 carbons. I only counted 9 in my group so far. So the 10th carbon, I'm gonna put attached to the double bond O for my 5th degree. 2 bonds to that carbon. Got a benzene ring here. Got some H's. This is B, and that's A, B, and that's A. And then I kind of like this idea of the methyl on an oxygen, kind of an ether-like group. This is peak C. And then D is attached together, the E. I'm thinking maybe attach it to something. I don't know. Here's a better idea. I now have my 4 puzzle pieces. Let's make sure it adds up to C10H12O2. I got carbon, that's 1, 6 more is 7, here's 8, 9, and 10, excellent. No H's, I got 4 here, plus 3 is 7, plus 2 more is 9, plus 3 more is 12. Good, that's a match. Do I have 2 O's? I got 1 here and 1 there. Good. These are all the atoms in the chemical formula. I got the number of degrees. That looks good. Let's see how you snap these together like Legos, like puzzle pieces. Well, this group only has 1 more bond. This group only has 1 more bond. They're on the outside of the molecule. So like the edge, the border of our jigsaw puzzle. These 2 pieces are in the middle. They're only 2 pieces. You have to snap these together. And I decided that peak A is farthest downfield. So I'm going to put this O with a pi bond. 2 things that are going to send these hydrogens downfield. If I connect it to the double bond O on this side, then A is farther downfield than B. These hydrogens are farther from oxygen, farther from that pi bond. Okay, and now, all right, put this piece to that piece. Now you decide this end piece, do you want it on the right side or the left side? The ethyl group, do you want on the right side or the left side? The only thing we have to help us is the position of these hydrogens. So if we put these hydrogens here, right, we say this, then these hydrogens are next door to a ketone. Or we can put it on this side. This is D, D, E. This is E, E. And these are B, A, A. And we already said the double bond O could be there. Okay, so either connect this end piece there. And now let's see which one the correlation table suggests. If I decide to snap the ethyl group to the carbonyl group, that's like a methyl ketone. The correlation table suggests that a hydrogen next door to a ketone, hydrogens next door to ketone should be between 2 and 2.4. So let's write that down. These should be 2 to 2.4 expected. That's what the correlation table is saying. And then right here, what if you put hydrogens on a carbon next door to benzene? These are benzylic. Is that on the correlation table? Allylic is. Yeah, it's right here. Aromatic methyl. Yeah, so if you have a hydrogen or 3 hydrogens, some hydrogens on a carbon next to benzene, now we're expecting a peak between 2.4 and 2.7. And what is peak D actually? Peak D is a big mess. Peak D is right here. It's almost at 3, so 2.9. So which one makes more sense? 2.9. It's closer to this one. So that'd be my educated guess. It's probably, it makes more sense to put the ethyl group here. So we get the correlation table to match. But again, gotta be flexible. It might be this one too. So I think on the exam, I would accept, well, I think I would give someone an extra point for this one. That makes more sense. This one, get everything except maybe half a point or maybe 1 point less. What's left to complete the molecule? Well, I already put the ethyl group on there. So now I need this ether group. So this is really close to the answer, maybe a half, maybe 1 point away. I would give someone full credit. Hey, that's not an ether, that's an ester. Oh, and assign the peaks. So this is peak C. Someone said, I'm going to choose this molecule. Well, that's pretty darn close. I'm saying it's probably this one. Cool, that's enough for now. Take a look at the videos on Canvas. I solve 2 more problems in one video, and there's something else on Canvas, I believe, to help you out. I know this might be the most difficult part, analyzing the hydrogen NMR, but it's the most rewarding, the most informative, the most helpful. So take some time, maybe rewind parts of this, get some practice in. I'll see you in the next video.